All right, hello everybody. So, got a little bit of a different tutorial for you today. So, we're actually going to talk about, well, I guess you could say it's SEM related, but we're going to talk about how to do EBSD. So, on our plasma FIB, we have an EDAX Velocity camera, and it is often used to do EBSD using just the electron beam um, of the dual beam instrument. So we're going to go over how to do that today and do a little tutorial for you here. Okay. So obviously there may be some differences with the setup between your system and and mine. The Velocity camera is kind of the newest model of camera I believe that EDAX has come out with. So obviously your EBSD camera may be a little bit different, some of the settings and whatnot. So just kind of keep that in mind. So mainly I'm making this for the people at my institution who use the system so they can have this as a reference. So all right, I already have the sample loaded in here. So let's talk about that. So let me go ahead here. Let's expand the NavCam quad. All right, so this is the multi-stub holder right here. And this guy is the sample that we're going to be looking at today. So this is an Inconel 600, so which is basically just it's a nickel-based alloy. It does have some other trace element, not trace I should say, but other elements in it, but it's basically just nickel. So polycrystalline nickel, and this has been mounted using well-dried carbon paint on a standard half-inch diameter pin stub. Okay, now this facet here of the multi-purpose holder. So your stage may or may not have one of these multi-purpose holders. I love these things. These are great. They can take a ton of these stubs in here, plus grid holders, right? And then you also have this side over here, which is pre-tilted 45 degrees, which is perfect for doing EBSD. Because as you're going to see here, we have to get the sample to a total tilt of 70 degrees. That's the standard angle for doing EBSD work. So this gets us already 45 degrees there. Okay, this is a different sample right here, which is not at all related to what we're going to be doing today. I just have it in there for something I'm planning on doing later. Okay, so anyways, this is the sample right here. So let me go back to for quad view. All right. So let me go ahead here, go to beam control, turn on the beam. So the first thing we can talk about here, I'm not going to turn on the ion beam because we're not going to use it today. I'd hit wake up if I was going to do that. All right, so first question we kind of have to ask here is what are the settings that we're going to use for doing EBSD, right? So voltage, current, okay? And this is a tricky question to ask, as is just performing any kind of SEM work in general. This can be a tricky question depending on what it is you're doing. Okay, so keep in mind that we have a field emission gun instrument here. So one of the things that means is that we can still form fairly small probes even when the voltage gets low. Okay, that we couldn't necessarily do quite as effectively if we didn't have a FEG, but we do have a FEG. You also have to keep in mind the effective operational range of the EBSD camera. So generally speaking, it's 10 kilovolts is kind of considered the floor when it comes to beam voltage for doing EBSD. Okay, I have not come across a lot of reports of EBSD being done below that. Okay, so that's kind of considered the floor, and then you could go up to as high as 30 kilovolts. So where would you want to go within that range? Well, generally speaking, because your interaction volume gets smaller, right? When the voltage goes down, right? All of the factors being the same, okay? Meaning, you know, my probe size is basically unchanged when I change the voltage, which is, you know, to a degree more or less true with a FEG, although not, you know, strictly speaking, not true, okay? Um, but your spatial resolution, including when you're doing EBSD, is going to tend to be better when the voltage goes down. The catch to that, though, is that the camera tends to respond more poorly when the electrons are lower energy. Okay, so that means your patterns are going to be harder for the software to analyze and to solve. Okay, so there's trade-offs here, right? Now this is a really good camera, okay, so that, you know, we do have that helping us here, and this is a good sample. So it's one of the reasons why we use this as a standard test sample. And nickel's good in general because it's fairly high Z, it scatters pretty strongly, so we can get nice patterns from it. Okay, so anyways, you know, that's kind of an existential question, right? What voltage to use? Again, I wouldn't go less than 10. So, you know, but the smaller, kind of the finer the microstructure, the more that tends to support you needing a lower voltage, just as a general rule, okay? So then the other question is, what kind of current do we want to use? Okay, so, and again, this has, you know, trade-offs and benefits as well, okay? So more current is going to give us more signal in the EBSD patterns, right? And that's going to generally allow us not only to get better quality patterns, meaning more signal in the patterns, but it's also going to generally allow us to index the patterns faster because we don't have to acquire the pattern over as long of a time period, okay, or an exposure time, okay? So the trade-off is, right, if you make the current bigger, you tend to get a bigger probe, okay, and that, depending on your microstructure, that could impact the spatial resolution, okay? Generally speaking, the higher you go in voltage, the less of an impact you're going to see in terms of the probe size on the when you're changing the current, okay? Especially when you consider the interaction volume that's resulting as well, okay? That's going to be more of an impact when you know, go down towards 10 kilovolts. Generally speaking, though, if I click on the little pull down list here, okay, you're generally up here in at least the nanoamp range to into the tens of nanoamp range, okay? So it's not unheard of to do EBSD up here, you know, 10, 20, even higher nanoamps, okay? So for the sake of argument here today, why don't we, let's just leave it at 20 and we'll leave it at 13 nanoamps, okay? And actually, I know EDAX, just as a general rule, they recommend 20 as kind of a good default voltage for doing EBSD if you're just not sure about your microstructure, okay? So we'll leave this at these settings right here, just kind of coincidentally. I didn't plan that, just happened to work that way. All right, let's go ahead and unpause here. I'm going to switch to full frame by pushing F5. Okay, otherwise the way you can change that is right here. No, where is it? This guy right here, okay? So you can do that from the view pull down, right? That switches between quad view and single view, okay, depending on which one you have activated. All right, so let's do auto contrast, see if we can see something. All right, we can't see anything. Let me go back here, see where we are. So we're right here. All right, let me get us a little bit closer. So I'm going to double click over the sample here in the nav cam. Okay, and then I'm going to go to the CCD quad and I'm going to drive this up. So now another issue here that we're going to talk about is the working distance when you do EBSD. So there is an optimal working distance for getting the best performance from the camera. This depends on the camera, depends on the system, depends on the installation. On this particular system, the optimal working distance happens to be 8 millimeters. Okay, that's where you get the most optimal camera performance. That being said, so I'm going to stop it, kind of well below 4 because we have to, tweak with this here. That being said, when the installation is done, it should be configured to operate effectively over a range of working distances. So it doesn't have to be perfectly at 8 millimeters in order to work. Okay, that should be something that is accounted for in the installation. But we are going to target 8 millimeters here today. All right, let me drop the dwell time here because we have a lot of signal. All right, so as you can see here, I'm magged out almost all the way. All right, so you can see here, this is the rounded edge, top edge of the stub. So what I'm going to do here is I'm going to find, okay, so this is the, basically, right, this is the middle of the piece here, okay? When you're doing EBSD, you obviously want to be away from the edge of the piece, right? So now we don't have to be perfectly in the middle here. And in fact, if we move in here, you can kind of see like there's some spots here that have some contamination. So this piece is actually kind of weird in that it's got some kind of coring to the microstructure. So the grains are a lot smaller in the middle than they are on the edge. And actually, we can kind of see right here. And we'll go over here. This hasn't been kind of singed too badly yet. All right, so let's go ahead and mag in. And now I'm going to use my focus knob to get a good focus. And now you have to remember this is tilted, okay? So your focus you're always doing in reference to the middle of the screen, okay? And we'll talk about also what's called dynamic focus in a little bit later when we're actually running the map, all right? So I have a good focus here. Go ahead and click the UFO button. All right, so we're close here to 8 millimeters. So I'm going to go ahead and click 8, move us to 8. All right, that's good enough for now. All right, so now from here, I'm going to go to direct alignments and we're going to go ahead and tune up the electron beam since we're at the right working distance. We can see that the spot is already pretty well centered here. So we're good with the source tilt. Okay, next thing is the lens alignment. All right, I'm going to bump this amplitude up about, I like it closer to 50, but it's not too bad. Let's turn on reduced area here. Drop the dwell time a few clicks. All right, so this is close, but we can improve this a little bit better. Actually, let me switch to quad view there. Take a look here and see. All right, I think that's worse. So basically, I'm only seeing side-to-side movement here, more or less. So the area I'm looking at is shifting. That's not, again, not a concern. What you're only concerned with is how the image is shifting when it goes in and out of focus. This is basically okay. It's maybe going up and down still a little bit. Okay, and I might have overcompensated for that a little bit. But that looks good right there. All right, perfect. All right, last thing is the stigmation. So you can see, right, I'm seeing stretching as I go back and forth. So get the focus as good as I can, then use your stigmator knobs. And if you have a little blemish on the surface like this, this is perfect for doing this little hole. And actually, this can be challenging with a well-prepared EBSD sample because usually you're not going to have a lot of blemishes, right, on the surface of a well-prepared EBSD sample. All right, but we are all focused here. The image, the beam alignment is good. So what we need to do now, let me switch back here. I'm going to hit the UFO button. And all right, so we're basically right at 8 millimeters. All right, so now we have to tilt to get to 70 degrees. Okay, so we have to tilt 25 degrees because 25 plus 45 is 70. Okay, but 8 millimeters, those of you familiar with the system will know this is not the eccentric working distance, okay? We are not at eccentric height right now. So if we tilt, we are going to lose this area from the field of view, okay? The way to deal with that is you go to the navigation quad here, or the navigation module, and then up here in the stage panel, you're going to check ZY link, okay? What that's going to do is it's going to impose the eccentric position to be what it is right here, okay? So you're going to watch what happens here. If I tilt 5 degrees, and I'm going to go not straight to 25, just 5-degree increments, okay? So watch what happens when I do this. Let me switch to, okay? Okay, so you saw the image jumped up and then it tilted, but now when it tilted, this basically stayed centered, okay? So that's what this does by checking ZY link, okay? So I'm going to go to 10 degrees, okay? And then each time I'm recentering with a mouse click, okay? So it's pretty close here. It's a few micrometers off each time, but not a whole lot. Okay, so you can see, right, the surface is getting more and more tilted. All right, and then let me double click on it again. All right, so now here's where, because the sample is tilted really, really high, you have to be sure that whenever you're focusing in reference to the middle of the image, okay? Right, and that looks good right there. Let's hit the UFO button. All right, and perfect. We're basically right at 8 millimeters, and we are tilted 25 degrees, okay? Plus the 45-degree pre-tilt. We are away from the edge of the sample, so we are good to go at this point to insert the EBSD camera, okay? A few other things to mention here. So one of the things I'm going to do here is, where are we? Okay, right here, this is what's called a blank for the beam. Okay, what that does is it doesn't stop the scanning, but it just deflects the beam off the sample, so I'm not, building up contamination. Okay, some other things to note here. The plasma, or the PFIB that we have, it does have a built-in plasma cleaner. So if you go here under Tools, you do have the option to run a plasma clean. This can be beneficial to do, especially if you have a sample that's a little kind of tougher to work on. It doesn't kind of scatter as strongly, where having the presence of surface contamination is a little more detrimental. So this has a built-in cleaning procedure here. Okay, I'm not going to run it, but you could do it, right? So you could do it now. There's also a way to do it when you're actually pumping the chamber down after the sample goes in. Okay, so anyways, I'm not going to otherwise go through that. Right here, you see the CCD quad here. Okay, so before we insert the camera, you have to make sure that you are at the right conditions. Okay, so there's no interlock when we insert the camera to basically tell us that your conditions are inappropriate. You're risking hitting the camera when you insert it. Okay, so just something to kind of keep in mind. All right, so I'm going to leave the beam blanked here, and actually, I'm going to now switch over to, okay, so this is the EDAX computer. All right, so I'm going to go ahead and log in. And we're going to be using EDAX TEAM for this. And this, of course, just FYI, we're only going to talk about collecting the data. Processing EBS data could be its own video. All right, so I already have a project called testing, so I'm going to use that. Otherwise, you could create a project. Okay, and then, so then the way this works is you can set up samples within the project. Okay, so I already have a Inconel 600 sample in here, okay? But if I didn't have one, I could just click sample, and then I could, add it in here, right? But I already have Inconel 600, okay? The other thing to keep in mind as well, although actually, you know what? Just for the sake of argument here, why don't we I'm going to go back here. All right, so let's pretend I didn't log in. And I'm going to log in. Okay, we have EBSD selected here. See how it's kind of like lit up a little bit? Okay, now it's not lit up. There we go. Log in. All right, so I'm going to just start from creating a new project. So create a new project. All right, so project name. We'll call this project YouTube tutorials. Okay, sample Inconel 600. Let's go. We'll call YouTube EBSD tutorial. Okay. All right. So now what we have to do here is we have to tell the system to look for certain structures when it's doing the EBSD indexing. Okay. So we're going to click on this button to identify structures. It's going to pull up this periodic table. It will already have inside of it right now, or already defaulted, two just generic files, one for Fcc and one for Bcc. Okay, we'll get rid of those in a minute here, as you're going to see. All right, so the way this periodic table works is you can tell it which elements are in the structure that you want to find. Okay, so right now it's saying, well, maybe it's got every single element in the periodic table. Okay, all right, we don't need to do that, so we're going to click no. They're all going to be red. Then we can click on nickel till it's green, because we know that that's what the sample is, and then click search. All right, and then we see we only get one hit here, and this is exactly the structure of nickel, right? So it is a FCC. Okay, so we click on it, and then we click add here, okay, and then we have it in the phase list. Now, whenever you're doing EBSD, it's always best to use the least number of phases you possibly can, okay? So if we know the sample is just nickel, we don't want to tell it anything else, okay? The reason you don't want to do that is that can actually be detrimental to the ability of the software to solve the patterns, okay? Because it can get confused if two of the structures are really similar, okay? So it's always better to, give it the least number of possible phases. So if you know the material is one phase, only give it that phase. Okay, so I'm going to remove FCC and BCC, and it should also be noted that there is a way to input, if you don't find it here in the database, okay, there is a way to actually build a structure and put it in to the phase list as well. Okay, I'm not going to go through that, but that is something that can be done. I know that it works because I've actually done it. Okay, so we're going to click OK. But most of your, main, like common structures, I mean, the database is pretty extensive, okay? All right, then we're going to click OK. And now we're into the team window. All right, so now we want to insert the camera. Okay, so up here in the Advanced Properties tab, we have a bunch of stuff here. Okay, so the second one is camera position. And then this guy is going to insert it. Okay, so I'm going to go ahead and click this. And then I'm going to switch over to the other view. And down here in the CCD quad, we're going to see the camera come in from the right. I think it's going to stop about here. So the stop point is predetermined by the installation. That's not something that you have any control over. Okay, you just want to click that insert arrow in the upper right, and that will push it all the way to its endpoint. All right, there we go. All right, so I'm going to go back to full quad view. Okay, now that we have the camera inserted, did it pause? Looks like it paused automatically. Yes, you want to make sure that this is paused, okay? The reason you want to do that is that this camera can produce intensity that actually interferes with the EBSD camera, which you don't want, okay? So you always want to make sure that the CCD quad is actively paused when you're doing the EBSD once the camera's inserted, okay? So it's inserted, everything's safe, we can pause it and we don't have to worry about it, all right? Okay, so we're gonna come back here to the SEM image and we're gonna unblank the beam, Okay, and we see that our image is really saturated, and that's because we're getting additional signal from electrons that are hitting that camera because it's close now. So I'm going to just push F9 to do auto contrast and brightness. Okay, all right. So additional stuff to talk about. So we have a surface here that is highly slanted. Okay, so this end here is higher than this end, okay, by a lot, right? Because it's tilted 70 degrees. Okay, so the good news is we have a way to compensate for that, and it's called dynamic focus. Okay, so make sure you're in navigation, come down here to dynamic focus panel, and you just check dynamic focus. Okay, make sure that your pre-tilt is accounted for if you have any, which we do. We have 45 degrees. Okay, so now what's happening is as the beam is scanning, it is accounting for the tilt of the sample to try and keep the whole surface in focused. Okay, so one thing to keep in mind though is for this to work effectively, the dwell time usually has to be kind of long. Okay, so this is with let me run that again just to brighten it up. Okay, this is with dynamic focus off. So if I turn it off here, or on, I should say, if I turn it off, okay, so that's pretty obvious actually. You can see how it gets blurrier at the edges, right? When I turn it on or turn it off, okay? Right, so you always want this on when you're doing EBSD, and again, you want the dwell time to be kind of long here when you're doing this, okay? All right, so now that we're scanning the area, another good question to ask is how wide do we need to make the field of view here when we're doing the EBSD mapping, okay? So generally speaking, you know, you want it wide enough to get a large number of grains in your analysis area. I don't know what the, I know there's like a recommendation from EDAX about that, right? Because if you make it too big relative to the grain size, then you don't sample the grains effectively enough, okay? But if you make it the analysis area too small, meaning the magnification is really high, you sample the grains well, meaning you have a large number of pixels per grain in the map, but the total number of grains that you analyze is also then not large enough. Okay, so there's kind of a sweet spot, if you will. Okay, so what I'm going to do here, because I kind of have an idea about the size of the grains here, I'm going to put this at, let's see here. No, I'm going to go indicated. Yeah, we'll go indicated 2500. Okay, because I know that's kind of a good setting here. Okay. All right, so let me switch over to the EDAX side now. All right, there we are. All right, so camera's in, and now we're going to talk about setting up your EBSD camera parameters. So this is a critical element of getting the most accurate result and the most optimal result when you're doing EBSD, okay, is how do you set up the camera? So there's a whole bunch of stuff in here, and we're going to kind of, take this in parts here and try to get through it all, cohesively, hopefully. All right. So this right here is your live pattern. We're not really seeing anything right now, which I'll explain why in a minute. This right here is your frame rate or pattern rate. Okay, so right now it's saying that we are acquiring 1,000 patterns per second, okay, or frames per second. This number right here is the pattern intensity fraction, okay? So this goes from 0 to 1. I think that's the correct terminology, is intensity fraction, okay? Or sometimes people just call it intensity, okay? But this goes from 0 to 1. So the higher this is, the more signal you're getting in the pattern, okay? Right, and this is controlled by exposure, okay? So you can see what happens here. If I increase this, right, I'm getting more signal in the pattern, okay? But, right, because this is going up, but I'm also getting a hit here in terms of the speed, okay? So if I make the exposure time shorter, my speed goes up, the intensity in the pattern goes down, okay? So I lose signal. right? But if I go the other way, I lose speed. Okay, so there's kind of a trade-off. Now you'll notice there's only exposure in here. Some of the older cameras, there was a gain setting. On the Velocity, there is no gain setting. Okay, there's only an exposure setting. Because of the design of the camera, it's a CMOS camera. Okay. Let's put this back here to about 1,000 frames a second. Anyway, just for for the moment here. All right. Binning. So binning refers to the pixel resolution of the pattern, okay? So 4x4 is usually is the default, and this goes from 1x1 to 16x16. Okay, so as I go lower binning, I end up with more pixels in the pattern, okay? So now a really neat consequence of this being a CMOS camera is that if I go from 1 to 4, or 1 to 2, or 2 to 4, I don't really get any change in the pattern intensity. Okay, so let's watch what happens when I go to 2x2 here. All right, give it a second here. Okay, all right, so you can see, right, my pattern intensity basically didn't change. Okay, and again, that's a consequence of the camera being a CMOS camera. Okay, let me put it back to 4x4 here. Okay, but now what I found here is if I go from 4x4 to 8x8, okay, I now actually do get a change in the pattern intensity. Okay, so again, when you change the binning, you're changing the summing of the pixels. Okay, so now we're doing a summing of the pixels. So when you're between 1 and 4, changing the binning doesn't change this intensity. But when I go from 4 to 8, or now if I go from 8 to 16, okay, every time I increase the binning, I actually end up gaining intensity. Okay, and so the reason that's important, right, is that gives you a way to increase the intensity of the pattern without changing the speed. Okay, so that's why that's important. Okay, that's an option. So, an existential question here is, what binning do I use when I am collecting my maps? Okay, so I think EDAX recommends 4x4 just as a general, setting for doing that. Okay, I think they recommend that you go to something higher like 8x8 if you're planning on actually saving the patterns as part of the post-processing. Okay, the other option, the other thing too, of course, remember is that, and maybe this will make a little more sense later, is that if I increase the binning, I don't have the same number of pixels, so the patterns look grainier, right? They don't have the same resolution, so that can also make it a little more challenging for for them to be indexed correctly. Okay, so again, trade-offs, right? Everything has a trade-off. Okay, all right. For now, let's just leave it at 4x4 here. Okay, and let's leave this down here at what it's at right now. So for this exposure, which is giving us about 1,000 frames a second. Okay. All right, so for the mode, okay, what is mode here? So mode, basically, this changes, I think, the bit range of the camera. Okay, so standard mode is, I believe, that's 12 bits, I believe, for the patterns, okay? So 12-bit dynamic range. If you go to high speed, that cuts it down to 10, and what happens then is you can actually get even higher frame rates, okay? There's also an option here to go to super mode. If you go to super mode, that cuts the bit rate to 8. Okay, so again, you're losing dynamic range, but your exposure time can get less, and your frame rate can also get higher. Okay, so again, trade-offs, right? But in standard mode right now, with full bit range of the camera, we're already getting 1,000 frames a second, okay, which is, pretty good, okay? But this is capable, I believe, of going all the way to 6,500 frames a second at its max rate. Okay. All right. So we'll leave this here. image processing. Okay, so this is the digital processing that is done to the pattern. Okay, so there's a bunch of different recipes that you can use here. If you're working with a polycrystalline sample, and this is important, okay, because you have to stipulate that, because this is very sensitive to, if you're talking about working on a single crystal, working on, a polycrystalline sample. But generally, if you're working on a polycrystalline sample, enhanced is a good one to use as default. Okay, so we'll put this in enhanced here. Okay, and now that we have all of these settings done, now what we need to do is capture background. Okay, so let me go back to the SEM image. Okay, so this is the area we're scanning right now. Okay, we want to make sure that we're using a long dwell time, right? So our dynamic focus is good, and we're scanning the whole area. Okay, and we're going to go back to the SEM or the EDAX side, and then we're going to click capture background. So you have two options here. Okay, so if you click smart, what it does is that it expands to outside the area you're scanning for the background. Okay, if you do SEM area, then it just limits it to the area you're looking at. Okay, so if you're not sure about your proximity to other features, like if you had on the other side, like you were close to the edge, right? Obviously, you don't want an edge in your background, okay, or an open area in your background, okay? So in that case, you would want to do SEM area. So SEM area is just, as a default, is probably the safest one to do, okay? So we'll go ahead and do that here. But Smart has the advantage just of, sampling a wider area potentially. All right, so we'll go ahead and do SEM area. If this was a sample, for instance, where we had, it wasn't like you had, it wasn't homogeneous, you had different regions of stuff, you had like voids and things, or, holes or whatnot, you might, anyways, I'm kind of blabbing here a little bit, but anyways, yeah, you have your area there. It's usually just best to do SEM area. Okay, all right, so now we are going to collect a survey here, survey image. So I'm going to click survey up here, and then I'm going to click image area, okay? So when you're collecting a reference image, you have a couple options here. So this ACD is going to use the same image. You're basically going to get the same image that you were getting on the SEM, okay? So this is usually just the best way to go here. FSD can be useful to kind of show the microstructure a little bit better, but whichever one of these you pick, it has no bound, or has no bearing, I should say, on the actual map collection itself. Okay, so keep that in mind. So I'm just we'll leave it at ACD1, and then we'll click image area. All right, so there we go. So we acquire a reference image now. Okay, and then it's going to put this green circle right here. So this is the beam position, and this is the pattern for that beam position. Okay, so as I drag this around, you can see the pattern change, right? Because I have a polycrystalline sample here. Okay, so what you want to do here is you want to find a good pattern, and that's really easy to do because these are all really good. And once you have a good pattern, there we go. And we'll leave it right there. You're going to let go. Okay, it's going to pull up this pattern window right here. Okay, and there's a few things to touch on in here. So if we expand this settings tab on the right, there's a bunch of stuff in here, and I would love to do a deep dive on all of this, which would be a really good thing to do at some point. But for now, really the only, or not, I shouldn't say only, but the most important thing to keep in mind here is in this HUF, this HUF menu, you want to make sure you have the mask set to the proper value. Okay, so the mask, without going into it, so this is one of the many things that it's using when it's solving the patterns, okay? But this is very sensitive to the voltage that you're using on the SEM, okay? So depending on your voltage, you need to change this. I know from experience that for doing 20 kilovolt work, medium 9x9 is perfect, okay? Generally speaking, if you click on this, you can see the different options. When the voltage goes higher, you're going smaller, okay? Voltage goes bigger. Yes, voltage goes higher, you're going smaller. voltage goes lower, you're going toward larger, okay? So if we go to something like 10 kilovolts, I think medium large is more appropriate at that point. Actually, I have a little table over here I can take a look at and see. There we go. Yeah, medium large at that point, okay? So anyways, so this is probably the most important thing. Make sure you just have this set correctly. Okay, once it's set correctly, you want to evaluate the result here. Okay, so you're seeing here now the solved pattern or the solution superimposed on top of the pattern right here. Okay, so you want to make sure that this makes sense, right? So this second button here, you can actually toggle this on and off, and you just want to do a sanity check, right? You want to make sure, does this look good? Does everything line up? And it looks really, really good here, okay? Just like we would expect for this kind of a sample, okay? Another thing we can do is we can do a tuning to the result here, okay? So if we look down here, we're seeing a couple of useful parameters here. So one is the confidence index, which tells us basically how confident the system is that this is the solution. So this goes from 0 to 1. I think they consider anything above 0.1 to be a high confidence. So obviously this is really, really high. And then the other parameter here is the fit. And I think anything less than, I think 3 degrees is the number. I'd have to go back and check. They consider, to be a good fit. Okay, so obviously this is also really good. Okay, but there is an option here to tune this result. Okay, so if I click this little guy right here, okay, and sometimes you can see a little bit of a change in the solution, but it's usually not like dramatic. Okay, but yeah, it didn't really change the confidence of the fit very much. Okay, but anyways, we have a good result here. We can go ahead and save this pattern by clicking Save Changes, and then if we want to send it to the project, we can actually click that little arrow, and we can close the window. So now we can see here we added that spot in there, okay? I don't think you have to save the pattern in order for those changes to take place, and actually, in fact, over here on the Advanced Properties, you can see there's also a Huff tab right here, right? And you can see all the same stuff, right? I think if we click full display, right, we can also adjust the mask here, okay? Again, at some point I'd like to do a deep dive into this, but we'll just leave it alone right there for now. All right, so I'm going to release the beam here for a minute, okay? And so now the SEM has control again. And let me go back to the SEM for a second here. Sorry, let me silence my phone here. All right, there we go. All right, let me go ahead and do auto contrast. The reason the image keeps getting darker is because I know we're getting some contamination on there. All right, one of the things I've kind of noticed periodically is that when you switch control back and forth between the SEM and EDAX, sometimes the focus can kind of get a little off kilter. So it doesn't hurt to kind of mag in here and just make sure you're nice and focused well. I mean, it didn't really change at all, so we're good here. All right, so we'll go ahead and we'll go back to 2500 indicated, just like that. All right, and let me go back to the EDAX side. All right, so a couple other things here that I needed to mention here. Okay, if we click this image area tab in advanced properties, you want to make sure that you have pre-tilt 45 degrees input here, and you want to make sure you have tilt correction also input here, okay? And actually, we needed to check that before we actually imaged, okay? We probably should have done that at the beginning. In fact, we should have done that before we imaged, but it was already checked, so we know that it was good, okay? That just ensures that the image has the proper scaling in both directions, okay? And this also ensures that the system knows that it's at 70 degrees of tilt, okay? So if you don't input the correct pre-tilt here, then the system does not solve the patterns correctly, right? Because it solves them thinking that it's only at 25 degrees of tilt as opposed to 70. Okay, so that's important. You have to make sure that these two numbers add up to the actual tilt, which of course is 70. Okay, all right. So go ahead and unblank the beam. All right, so a couple other things here before we do the map. If you click on EBSD mapping, there is an option here to save the patterns, okay, while it does the map. And this can be useful for post-processing, okay? When you're doing like data cleanup, there's something called pattern averaging that can really improve the quality of your data. And to do that, you need to save the patterns, okay? I'm not going to do that here just for purposes of making sure that we don't generate a giant file size, because that's what's going to happen, right? You're saving a pattern at each pixel. So in that case, you're going to end up with a ginormous file size. All right. But what I really wanted to do here was come back to these camera settings, and let's play around with this a little bit more here, okay? So that was at only 0.15 of the pattern intensity, okay? So let's just see here, for the sake of argument, let's just see, I'm going to drop this down here up to 0.1, okay, for my pattern intensity. Now look what happened. I gained 500 more frames per second, okay? And now because I changed this though, I need to do another background, okay? So we'll do SEM area again. All right, and then I'm still in survey, so I'm going to click take beam. And we can see that even at just 0.1, okay, at these conditions with this sample, I'm still getting some really good patterns, okay? So the takeaway from this is that with this camera, there really isn't necessarily an optimal number for this pattern intensity. It's almost to an extent like how low can you get away with while still getting, a good pattern out, right? You can see we're still getting very high confidence index here, good fit, but we gained, 50%, right, in terms of the speed, okay? So there really isn't an optimal number here, right? Depending on your sample, though, you may need to make this a lot higher, right? So, I mean, now there's nothing that says we can't make it higher. If we make this, maybe we can make it 0.4, okay? And you can see what's happening now, right? I'm up to, or down to 350 frames a second, okay? All right, so let me go ahead here. Let me release the beam. Okay, and then I'm going to do another SEM area, and we should see this wash out here. Even though it looks bad now, it should wash out once we do a background subtraction. Yep, there we go. Okay. All right. And so you can see now, yeah, we have a really good patterns now, okay, because we've got way higher intensity, okay, 4 times as much as we had before. But you can see, right, my frame rate is now 1/4 what it was. Okay, so again, everything is a trade-off here, right? But again, people always want to get things done quicker. Okay, so let's go ahead and we'll drop this back down. So I'm going to drop this back down until I get to 1500 seconds for the exposure time, or 0.1 for the intensity. Okay, so right about there. Release beam. All right, do another SEM area. So anytime you change any of the camera settings, you have to do another background. Okay, keep that in mind, because the next thing we're going to do here is we're going to mess with the binning. Okay. All right, so let's see what happens here. Actually, let me take beam. Yeah, so this is back to 0.1. Okay, and you can see, hopefully that's kind of obvious here, right? The patterns are not quite as good, right? Because signal to noise is not as good, but these are still easily solvable. Okay, we're still getting really high confidence here. So even though the signal in them is not as high, right? Because we have a good sample, and because we're at higher voltages, we can often get away with you know, a really short exposure time when we're doing this. All right, let's go ahead and release the beam. All right, so let's drop this, or I should say increase this. Let's increase this to 8, okay? All right, so you can see now I gained intensity. So now what I could do here, because I gained intensity, is I could drop this exposure time down even more, okay? So I could go probably to 3,000 frames a second to get the same intensity, but let's actually leave it at about 2,200. So I'm at 0.3, okay? And again, yep, let's take another background. Oops, actually, I need to change something here. I forgot to put this back to enhanced. Okay, all right, let's do that now. All right, let's go ahead and take beam. Okay, so we can see even at 8x8 binning, I'm getting a good pattern here. Okay, so now hopefully you can kind of tell, right? This is definitely grainier than what I was seeing, okay? But even though this is kind of grainy, the software and the computer are not going to have any problem indexing this, okay? You can see right here, right? It's finding the bands really, really easily, okay? So don't be afraid to try, you know, increasing the binning here, okay? And especially if you plan on saving the patterns, I'd probably use 8x8 binning if I was going to do that, just for purposes of, you know, keeping the data set, you know, manageable size of memory, okay? All right, so actually, why don't we leave it at 8x8? Okay, we'll leave the camera at this setting here, okay, because this is going to allow us to run this map pretty quick. All right, let's release the beam. Okay, and then I'm going to go back to the SEM side one more time. All right, so we can kind of see now, hopefully, that the image does look a little bit out of focus. Okay, so I don't know why that happens sometimes, but sometimes it does when you switch between the when you switch between EDAX and SEM control, sometimes the focus goes out. All right, so from here, we are ready to run the map. All right, so we are going to, I don't think there's anything else I forgot over here. We talked about making sure the tilt correction and pre-tilt were good. We talked about saving the patterns if we wanted to. You know what, actually I'm going to do? I'm going to save the patterns just because I can use this data set later if I do a tutorial for data processing. Okay, so I'm going to save the patterns just in this instance. And again, it's 8x8 binning, so it's not going to be, you know, terrible here. All right, and we'll go to mapping. All right, so now you do have the option here to select an area to map. I don't recommend you do that because I've seen this cause issues with map distortions if the whole map isn't selected. That might be a bug that they fixed at some point, but I'm not sure. Okay. All right. So here under resolution, we have 3 kind of defaults here. So if you're trying to get, you know, your best quality, I would go fine, obviously. Okay. You do have the option to input a custom step size if you want. Okay. But usually I just default it to fine, and that works well. It calculates the step size on fine based on the horizontal field width. Okay, so let's do a little math here really quickly. Okay, so we've got 650,000 points in the map. Okay, so if we do, all right, so we're gonna do 650,000. And we're at 2,200 frames a second. All right, so according to my calculation, it's only going to take us about 5 minutes to run this map. Okay, that's it, right? So that's really, really quick. Okay, so let's go ahead here and we will click collect map and see what we get. Whoops, oh my goodness. I can't believe it. I was not on here when I did it. Okay, let me go back here. Sorry, I jumped the gun. All right, I'm going to go ahead and delete this. So I took one line of the map, but then I realized I didn't have the input correctly. All right, let me go ahead and delete this because There's nothing there. All right. So anyways, we were here in survey. Okay. Then I clicked on map up here. Okay. So I was saying here, you do have the option to actually select an area, but I don't recommend you do that because I've seen that cause issues with distortion of the map. Okay. Now, if you mess this up, you can just click this guy, it will re-expand it. Okay. So generally I say just do the full frame. Okay. Now, if you mouse over collect map, you have options here for the resolution. Okay. And obviously I would go with fine. Okay. If you're trying to get the best quality. Okay. So now right here, you can see where it says the number of points in the map. Okay. So about 650,000. So if we do 650,000 divided by 2,200 patterns per second, we end up with about 300 seconds for the map. Okay, so again, this is telling me we should be able to run the map in only 300 seconds. Okay. All right, really quickly here, let me switch back to the SEM side. Make sure my focus looks good. It does. Yep, looks good. Make sure you go back to the same mag you were at, 2500 indicated. All right, and then we are ready to go, and we will click, whoops, make sure I keep this back. All right, and then click collect map. Now, the SEM reference image here that EDAX takes doesn't look very good, okay, but don't be put off by that. This isn't really going to impact the map itself, okay? That's just a result of the digital processing that it does, but trust me, the EBSD data is going to be fine. Okay, so while it's taking the map, down here we have a few things we can talk about, okay? So in the little smiley face here, I think that's what EDAX calls it. So we're seeing this green progress bar. So this is telling us the confidence index as a function of the line within the map, okay? So green is good, right? Green means you have an average confidence index that is, pretty high, okay? Which is what we want, right? And it's telling us right now we're indexing, close to 2,000 patterns a second, okay? And then if I click on these two guys, I can actually see the live pattern as the probe is scanning, and I can actually see the solved orientation for the unit cell for that position. Okay, again, in real time as this is happening. All right, so what we're seeing right here above the image as the probe scans is we're actually seeing an inverse pole figure superimposed on an image quality map, which is why you have IPF here and IQ here. So we'll talk about both of these in a second, but I'm just going to turn off IQ here for a second. All right, so now I just have inverse pole figure. All right, so what an inverse pole figure tells me is the set of crystallographic planes that is running parallel to the surface as a function of, color, right? So because this is cubic, I can represent all of this in one of these little triangles here. So between shades of red, blue, and green, okay? So that's an inverse pole figure. That's kind of one of the standard pieces of data that you get out of doing an EBSD map. All right. So if I uncheck that and I check image quality, okay, so image quality is a little bit misleading because when they say image, they really mean pattern, okay? So they're using some sort of metric to assess the quality of the pattern that is being acquired, okay? So what you can see here is when I go inside of a grain, I have a bright, right? I have a bright signal, meaning my quality is high. And then when I get towards a grain boundary, my quality is not so good, okay? Which makes sense because I'm getting contributions from both grains and I'm probably getting, some distortion to the pattern because of the imperfections at the grain boundary and whatnot. So this is entirely expected, okay, to see here in this image quality or pattern quality map. Another map we can generate is what's called a confidence index map. So that confidence index parameter I told you before, right? So again, green is good, okay? Green is high, and then red is bad, right? So we can see in the middle of the grains, I'm having basically solid green, and then as I get to the boundaries, I start to see a lot more red, okay? And that's exactly what we would expect, right? Because it's hard for the system to have a lot of confidence solving a pattern if, for instance, it's at a boundary and it's getting contributions from 2 grains inside of that pattern, which is exactly what's happening when the probe is at a grain boundary. But for now, I will just leave it right here on the IPF map, the live IPF map. So you notice, right, there's speckling here along the boundaries, okay, because it's having trouble solving, understandably, the patterns at those boundaries. So this is stuff that can be dealt with in post-processing, which, you know, hopefully I will eventually get around to doing a video specifically to cover that, because that in itself could be its own video about how to post-process EBSD data using what's called OIM, which is very, very powerful software, okay? And also keep in mind, because we checked over here, because we checked save patterns, okay, it is saving the pattern at each pixel while it is doing this, okay? And again, that's useful for, you know, doing post-processing. That tends to be more useful when your patterns are poor quality, okay? So, and that usually means like you're using low voltage, okay, or you're using a lot lower current, okay, which we're not doing here, right? But I wanted to do that anyway, just to show you how that could be done. But otherwise, for this data set, I wouldn't have otherwise saved the patterns, okay? And again, you know, if you're getting good patterns, you don't anticipate a need to use them in post-processing, I wouldn't save them, because again, it's just going to make your data set really, really big. You notice here, it's only giving 1 phase, right? Because we only told it 1. If there was 2 phases here that it was looking for, it could tell us which phase was each as well. But since we only told it to look for nickel, that's all it's putting in here. All right. And now it's going to pull up a little synopsis of the scan once it's done. Okay, and it's going to say your scan is complete. We did this number of points. We indexed this many of them, which is basically the same as the number of points usually, unless your pattern is just, or your sample is just really, really poor quality. Okay, so it basically, you know, indexed all of them. So a high percentage with high CI, right? Again, 0.1 is considered high confidence index. It's telling us the average confidence index, which again is really high, and again the average fit. So that fit was that angle number I was pointing out in that pattern window, right? That I think I said if it was below 3 was considered good, okay? And because we only told it nickel, it's saying your sample is 100% nickel, right? Then we click OK. Okay, so that is a basic tutorial about how to do EBSD here. And again, this doesn't talk about, you know, the ins and outs of data processing. That will be its own video at some point later. All right, go ahead and click finish here. Okay, all right, when you are done doing EBSD, by far and away the most important thing to keep in mind is to take out the camera, okay? So again, you come here to advanced properties, click camera position, and you click retract, okay? So let me go ahead and do that here. Okay, let me go back to the SEM side, unpause this guy. We might be able to see it still. Oh, we missed it. Okay, I didn't get to it quick enough. Okay, all right, but I can hear the motor going. I don't know if you can hear it through the microphone, but you're waiting for the motor to stop before you do anything else. Okay. All right, here's the SEM image. I'm going to go ahead and just pause this so we're not pasting the sample further. All right, motor's still going, I can hear. All right, okay. So then now, when you're finishing up, okay, make sure you uncheck this ZY link button. Okay, do not leave this checked for the next person, or it's going to throw that person off completely. Okay, he or she will be very, very confused about why the stage is doing crazy things when you tilt. Okay, so you have to be very careful. Okay, otherwise, finishing is no different, right? Just uncheck this. You go to stage pull down, home stage, turn off the beams, vent, all that good stuff. Okay, all right, so that's going to conclude the basic EBSD tutorial, and glad I was able to get around to this, certainly. And at some point, I will, as I said a few times here, get around to doing a tutorial about processing the data too. Okay. So let me know if you have any questions, comments, requests for other videos, of course, and look forward to hearing from you guys and seeing you guys again soon.